So to finish up chapter 19.3 in this video, 19.3 focuses kind of on two things. On the formation of Earth, and then the importance of the atmosphere. With the Earth, millions and millions of years ago, when the Earth was first forming up and planetesimals were still slamming into each other and colliding, it was really, really, really hot, right? All of those collisions make a lot of heat because of a lot of friction. So that's why I've got liquid potato written down, right? At one point in time, the Earth looked like a liquid potato because it was a misshapen, kind of egg-shaped, weird-looking planet that was mostly molten rock, right? Molten magma, like the lower layer of our mantle still is today. And it was liquid, it was molten because of all of those collisions and because of some radioactive material that was slowly decaying and giving off a whole bunch of heat through fission. Eventually that started to cool down and gravity started to pull things in to form a solid sphere. And that solid sphere is basically what the Earth looks like today, right? But the fact that at one point the Earth was liquid is what allowed it to differentiate. And differentiation, which I have, kind of squared over here, is the process where dense materials can sink to the bottom and the light materials, the less dense materials, go to the top. But this only occurs in liquids, right? If you have two solids, right? If you have a solid material here and you have a solid material here, two solids are never going to move through each other, right? They can't, this one can't get up through here, this one can't get down through there because they're solids, right? So the fact that a planet, when we, if you start to, drill down into a planet or you do some seismic investigations, if you discover that a planet has layers, right, like the Earth, it tells you immediately that that planet was at one time liquid. If instead you open up that planet and you find that it's totally random, right? There's no rhyme or reason. It's not differentiated into layers based on density. It's just totally random on the inside. That tells you that from its creation, from the very beginning, it was solid. It was frozen. So Pluto is like that because it's way out in the solar system, way far away from the sun. It was never liquid. It was always solid. So as planetesimals crashed into each other and formed up a larger planet, assuming Pluto is a planet, as those planetesimals slammed into each other, they froze basically in place and never got the chance to get hot, liquid, melt, and mix together and then differentiate. So if you see something that's differentiated in layers, you know that at some point it had to be liquid. This is the example with the Italian salad dressing, right? When you pick it up and it's been on the shelf for a while, it's in layers. And the reason that it's possible for it to be in layers is because it's mostly made up of liquids. You shake it up and that undifferentiates it, right? It now is all mixed together. You put it on your salad. And if you froze it, made it solid, it would now be totally random. But if you let it unfreeze, go back to liquid, it'll then differentiate again. So for the layers of the Earth, basically, we all know that there are three main layers of the Earth. There's the crust, which is very, very thin. It's like the skin on your body. The mantle, which is divided up into two layers, the upper and the lower. The upper is dense rock. The lower is the magma, right, where volcanoes and stuff comes from, and it drives the conveyor belt of plate tectonics. And then there's the core, which is solid nickel and iron, very dense. The heat that is still in the lower mantle, where the liquid hot magma is still coming from that fission. There's still some radioactive decay occurring, and that is causing the mantle, while it's slowly cooling, it is still liquid at this point today. That hot liquid, that hot magma, is moving in convection currents, right, where the hot material, less dense, moves to the top, it cools down and slowly sinks back down to the bottom. That is, in some places, driving apart tectonic plates, right? And in other places, if this plate, that's an ugly plate, if that plate and that plate are moving away, at another point, this plate will run into this plate. that could cause, if two plates run into each other, that'll cause a mountain to form. If they separate from each other, that'll open up a fissure, or could cause volcanic activity. If two plates slide past each other moving in opposite direction, that would cause earthquakes to happen. So I kind of skipped down to here because it's connected. So that was number one, kind of talking about the Earth's formation and differentiation and why we have layers. The second thing that the chapter talks about is the atmosphere and why the atmosphere is important. A very long time ago, the Earth's atmosphere was really, really hot. That was because it was formed up mostly of water vapor and a ton of carbon dioxide, not much oxygen. And so with a lot of carbon dioxide, the atmosphere got really, or the climate rather, got really, really hot. What's interesting is that any planet in our solar system or any other solar system that has a really thick atmosphere gets really, really warm. It makes sense. It's like putting a blanket over that planet. So we've got evidence of climate change and global warming from pretty much every planet in the universe. If you have a thick atmosphere, you get really, really hot. If you have a thin atmosphere, you're going to get colder, at least when you're facing away from the sun. So we're right in the sweet spot where we have a thick enough atmosphere where we're not too cold, but it's not too thick where we're going to get so hot and then all the ice is going to melt, etc. So the reason that this atmosphere is important is because if we remember back to chapter 18, we know that the atmosphere blocks a lot of incoming radiation from our sun as well as other stars. That radiation can be X-rays, UV rays, gamma rays, all sorts of radiation that would otherwise kill us. So without the atmosphere, life wouldn't have formed. Early life formed in the ocean because the ocean basically acted as the first atmosphere. It covered the whole world, and it also blocks much of incoming radiation, which allowed life to evolve and adapt in the, under the water, in the ocean. Once the atmosphere had built up, life was actually able to move on to dry land where it was no longer getting shot by UV radiation as much and X-rays and gamma rays. So without the atmosphere, no life would exist on planet Earth. That's why chapter 19 makes a big deal of that atmosphere. Without it, there is no life. So to do a 30-second wrap up of chapter 19, basically we've got number one would be the solar system forming, because we've got opposing forces that then collapse in. The nebula collapses at the center. It gets really hot and forms a star. At the outside, you've got planetesimals colliding to make planets. We've then got a couple laws, Kepler's 1, 2, and 3, as well as Newton's law of gravity, explaining why and how planets are in motion, that they move in ellipses, that they move faster when they're closer to a star, and basically why they don't go shooting off into space but stay in orbit, which is gravity. This also brings us to the conclusion, or the big point here, of that we can apply Kepler's 3 laws to other solar systems and other galaxies and look for planets that are in the Goldilocks zone. So that's kind of number 2 if we combine all that together. Number 3 talks about the sun, the different layers of the sun, what's kind of happening in those layers, and the big picture here is nuclear fusion, which is what's powering the sun and what would be great to capture on Earth and be able to use for a clean source of energy. The 4th main point is the formation of the Earth from a liquid potato into a solid sphere, and it goes from a liquid to a solid, which allowed differentiation to happen. And 5th and final is the atmosphere and why it is so important.